Hello everybody, and thanks for having me here. My name is Alfonso Oliva, and today I'm going to introduce you to some of the work that my group LERA Plus has been conducting with Universita La Sapienza, as well as some project applications at LERA. The first thing I would like to do is to actually answer three questions you might have. The first one being, what is LERA? The second one, who am I? And the third one, who is LERA Plus? After this brief introduction, we'll be moving into the heart of the presentation, and as mentioned before, we'll be taking a better look at how structural engineering has been integrated in the architectural workflow for the particular study of the Origami research that we are conducting with La Sapienza. We'll then focus on some of the research that we applied on projects work at LERA, and in particular, we'll take a closer look at some of the processes implemented in our design workflow. These processes, in fact, are very flexible and can potentially be later on applied to the research on origami shapes. At the end, we'll of course leave some space for questions or comments that you might have. LERA is a structural engineering firm with headquarters in New York that operates with other two offices located in Shanghai and Mumbai. LERA's portfolio includes a wide variety of building types, and we'll now go through some of them just to give you an idea of the scale of our works. The first category, in fact, that I wanted to introduce to you is a building for office use. I selected a few projects here. We have World Trade Center Tower 4, Shanghai World Financial Center, Lotte World Tower, and Bitexo Financial Tower. You're most likely going to be familiar with some of these structures, but in case you are not, it's probably going to be a good occasion to learn more about some of these very interesting structures. Let's then move into residential and mixed use. Again, very quick introduction. We have WJ Marriott Hotel Hanoi, Espirito Santo Plaza, and Loda World Towers. We are also very much involved in the design of libraries and museums. In fact, we are the engineers for WJC Presidential Library, Pinkton Art Museum, and George Lucas Museum of Narrative Art that is actually currently under design. The last category I wanted to brief talk about is special structures. In the specific images, I'm showing a sculpture by Richard Serra in Qatar on the left side, and the Miho Bridge in Japan. We are in fact very proud of being the designers for some of the most renewed sculpture in the world, and we actually aim on growing our presence in such an inspiring field. I also just wanted to give you a quick introduction on myself to let you better understand what brought me here today. And for this, I thought I would actually start by giving you a quick overview of my educational background. I started my studies back in Italy, where I earned my diploma of surveyor and actually worked as a surveyor for several years while studying for my Bachelor of Science in Civil Engineering in my hometown. I later on moved to New York for a Master of Science in Structural Engineering at NYU Polytechnic Institute, and later on conducted the thesis research at Columbia University on the Northwest Science Building. I went back to Italy after that and finished my Master of Science in Civil Engineering, and after that I started working in New York. I came to New York 7 years ago, and I've been working here for 5 years. And during the second year of work, I decided I wanted to know more about architecture and computational design, so I applied for a Master of Product of Architecture and Engineering at Stevens Institute of Technology in Hoboken. I'm currently employed at LERA, where I work as a computational design engineer, and I lead the LERA Plus group. LERA Plus is an entity within LERA that aims on interconnecting and implement different fields in our practice. Technically, LERA Plus is a laboratory for engineering research and automation, and our interdisciplinary background and the different interests that we have let us interconnect different concepts and apply them in the engineering and architectural field. In fact, I want to summarize our field of research for you in the following way. Automation processes and software development are two of the fields that actually started the whole effort, and we later on quickly expand in other interesting areas. We are in fact exploring additive and subtractive manufacturing processes, and to date we have, besides myself, other 3 people in the office certified for that. We are also conducting some research on how to improve monitoring of buildings, and in addition we are looking into applying principles of human interaction, machine learning and robotics to our practice. Today, unfortunately, we won't go in depth in all of these topics, but I wanted to briefly present them to you to give you an idea of our field of interest and expertise. Okay, we'll now take a look at a video that actually shows the work in progress of LERA Plus on the Origami research project. I think it was December last year when I actually met with Michela in Rome, and we started talking about the gap between practices in the AEC industry. After taking a look at each other's work, we saw a space for collaboration and we went for it. So I received some of Michela's works on the origami that you're looking at right now, and we started talking, taking a look at these to see how we could actually integrate engineering thoughts in the workflow. This is one of the definitions that Michela has put together for the research project. It's already a very powerful algorithm, but we are aiming on making it even better by integrating engineering feedback. The aim of these grasshopper definitions is to actually replicate folding techniques by using the physics engine for grasshopper kangaroo. And the idea behind this research is to actually think about this origami definition as potential application for real-world projects. For that reason, we are looking into establishing a process flexible enough that can be later on adapted to a large variety of architectural systems. We are showing how we have connected the origami algorithm to finite element analysis through Caramba. There is a plugin for Grasshopper. And later on, we'll show how we visualize data as well as we export data in an Excel database. The reason why we actually want to be able to export data is to process it and to actually link our design spreadsheets to later on perform structural design. The results from the design stored in the database can in fact even be read back into Grasshopper and actually visualized on your model. In this phase of the presentation, we're actually showing the interaction with the Excel database. So we are changing the load condition and we are recording the stresses outside in the Excel database. Of course, the database that we are building is way more detailed than the one that you're looking at. This is just like an example. We are applying in this example like a simple point load in a particular shape, configuration of a shape, and we have definitions that obviously are more complete than this. We can later on visualize, in this case we are visualizing stresses, we can visualize displacement, as we'll show in a second. For this particular example, the displacements are shown, like the worst displacements are shown in red, and obviously the threshold is a little bit off, but you get the gist behind it. In this other particular case, we are going to show how we are also looking at frame structures, or stick model if you wish, and we're basically building the same exact models that we were looking at before, but instead of having a mesh model, we actually have a stick model. And what we are showing in this phase is actually how to read the data back from the database inside Grasshopper. So we have like 2 different shapes in this case, and we are reading like 2 different sets of data for this reason. And this is obviously all like interacting live. So the aim at the end of it would be to actually not only visualize data, but also visualize engineering design information. So information from the design. As I mentioned before, the idea behind it is to actually apply these definitions to different shapes. In fact, in this example, we have a triangular shape that it's like a different shape, and we are applying, we're basically showing the same kind of procedure that we followed before, just to give an understanding that the flexibility of this kind of approach. Okay, the next logical step in the presentation is to actually show some of the project applications we worked on at LERA, and that could be the reason for that, for showing you this, is actually because later on this application can be integrated in the research on the origami structure. This particular example that I wanted to show you is actually showing you how a parametric model can be connected with finite element analysis and then to an evolutionary solver to perform a genetic algorithm optimization. This process will explore hundreds of schemes, and at the end we retrieve the best performing set of solutions that can be used for a more in-depth analysis with either the software that we are using right now, that it's Rhino and Grasshopper with the use of Caramba, or with any other finite element analysis software like SAP 2000 or ETABS or whatever else you would like to use, you prefer to use. These processes, besides saving time in the exploration of different design solutions, they actually open to a new space that will not be easy to explore with conventional design techniques. We actually make large use of these techniques during the preliminary stage of the design, but we also implement them for studies on components of the building during the advanced stage of the design. The video is actually showing like all the iteration that the evolutionary solver is going through. I'm going to advance it a little bit to show you the results at the end. And as you can see at the end, we have a set of solutions down here that are actually like a set of best performing solution. You can reinstantiate every single solution, and once you are happy with your configuration, you can actually just export these in different softwares if you want to double check your results, or if you want to advance the design to a next stage. The next project I wanted to introduce to you is our interoperability platform. The application currently allows connection between 4 different software, and they are Rhino and Grasshopper, SAP 2000, and ETABS, that are actually 2 finite element analysis software that we most commonly use for structural analysis, and Revit through Dynamo. The platform allows for geometrical data to flow across different software and is actually being implemented to contain also analysis data. Here we have just a quick example of how a parametric model of a tower is actually being transferred from Grasshopper to SAP 2000. The same procedure can actually be followed for the other software I mentioned before. The data is actually contained in an Excel database that gets built in Grasshopper, and later on it gets read from the application that builds the model in the software that we choose. This is like an amazing tool, and we are actually using it daily in our company. It's pushed, it's actually used like in all our offices as well, and we are implementing techniques for automatic updates. The last project application I wanted to show you is actually the design approach that we took for a sculpture design that we recently worked on. The first stage of the design process combines the use of a packing algorithm and finite element analysis on a 2D study. The second part moves into 3 dimensions, and a genetic algorithm optimization is performed on a parametric 3D finite element analysis model. An initial design, that is the one that you're actually looking at, was given, and the aim of the study was to come up with a solution that would respect the vision of the artist, but at the same time have improved structural performance. For this reason, we started by tracing the boundaries of the sculpture, and later on to run a packing algorithm to come up with a new configuration. This packing algorithm has been later on attached to a finite element analysis in Grasshopper to measure the in-plane deflection of structure of the different structures under a unitary wind load case. A large number of solutions have been produced, and the 6 best performing scheme had actually been selected and compared to the base option. we are actually showing now how to come up with like a different solution. This process is shown manual here, but it has been automated later on for the application of the algorithm. We are going to see in a moment how like an example on how we actually implemented the finite element analysis in the process. And as mentioned, we applied a wind load in the in-plane direction, I will say, as you can see, and we were actually tracking deflection for each combination that we're coming up with. Out of these, we came up with 6 different solutions. We compared them to these. There is actually the base scheme. So we unitize the deflection factor in the x direction. That is the one that we just studied. We unitize the maximum deflection factor the maximum deflection in the y direction. And we also unitize the weight factor because we wanted to keep an eye on how much weight we were adding to the structure. The number of elements, we tried to keep it close to 110. That was the initial number of the members. And we, of course, added and subtracted some of them. Option 5, performance and layout, was actually the preferred scheme for the next step of the design. For this particular step, we actually moved in 3D space, and we aimed on optimizing the deflection in both wind directions, as we are showing in this quick example. In this case, the parametric analysis model was actually connected to an evolutionary solver to minimize the deflection, while we were actually varying the distribution of pipe thickness across the structure and also the bottom and top width of the structure. The results were, of course, the results of this optimization were actually double-checked in step with our more established processes and software, and we actually used our interoperability platform to do that. As you can see now, we are going through the different stage of the optimization process. Quick note about Galapagos that I actually haven't made. This is the evolutionary solver that we use. There is a plugin for Grasshopper. It's a component for Grasshopper, I should say, actually. And just a quick note about the interface here. It's pretty straightforward to see how our solution is actually converging to a value. Again, we are tracking the deflection of the system. And here we actually have all the solutions, all the best performing solutions. And as you can see, the value of the deflection is actually going down as we move forward because we're getting closer and closer to a solution. Then you can actually instantiate different configurations. And whenever you're done, whenever you're happy with your configurations, you can just like record that particular iteration. And then, as you can see, with our in-house software, we were able to build these in our more established software. With this, I conclude my presentation. I hope it was informative and interesting to you. Please feel free to share any questions or curiosity or comments that you might have. Thank you.